falls is a nice parabolic trajectory if you ignore air friction. If you put in the air friction, it changes it a bit, but if you dive on the moon, you get a nice parabolic trajectory. No matter how much you like to, you know, it's still a nice parabolic trajectory for your center of mass. So that's what all of this is getting at. And relevance for us is that for our two-body system, what it means is that we can just adopt a frame of reference where the origin is sitting at the center of mass. And as seen from any other inertial frame, that center of mass is moving in a straight line at constant speed, but as seen in the frame where that is the origin, the center of mass is just sitting there. In other words, we're always free to use the center of mass frame, where we just put the center of mass at the origin and go to the frame which is moving along with the center of mass, or in other words, in that frame, the center of mass is just sitting there, and the two bodies are orbiting the center of mass. That's what all this allows us to conclude, is that we're always free to just choose the center of mass frame. We can ride along on the center of mass. So, this means that we are free to ride along on the center of mass. And do all our calculations in an inertial frame that has the center of mass as the origin. Inertial frame, I mean a frame in which Newton's second law is obeyed. If I am in a rocket and the rocket has its engines firing and I let go of my keys inside the rocket, then even though there's no force on them, after I let go of them, they'll still accelerate to the floor, but that's just because the rocket itself is accelerating upwards, and that makes the keys relative to the rocket accelerate to the floor relative to the rocket. So that's what we call a non-inertial frame of reference. But inertial frames are ones where if you don't have a force on something, then relative to that frame, then there is no acceleration. So the center of mass frame, the one that has the origin of center of mass, is inertial. Newton's second law is obeyed in that frame. Otherwise, we have to use what are called pseudo-forces and so forth, which you do plenty of when you take mechanics, but which you avoid assiduously talking too much about in freshman physics because it just gets too confusing to people who are first meeting all this stuff. Okay, any questions? Let's revisit Kepler's laws then for the situation where we've got two bodies orbiting their common center of mass, as opposed to what we had before where we said, Kepler himself said, the orbit of a planet is an ellipse with the sun in one focus, but now we're going to realize that no, actually the sun has to move too. And so what we really have are that both orbits are ellipses with the center of mass as one focus. So Kepler's first law revisited. Both objects in a binary double star, double planet, moon and earth, mass in ellipses. With the center of mass as one focus of each ellipse. The center of mass occupying one focus of each ellipse. So you get something like, here's one of the ellipses, and here's the other ellipse. So let's say there's the center of mass, and it's always true that the two bodies are on opposite sides of the center of mass. In other words, at any time, if you draw a line between the two bodies, that line always passes through the center of mass. Because it has to, because the center of mass lies on the line joining the two bodies always. And furthermore, it is true that both ellipses have the same eccentricity, so they're the same shape, they're the same squishiness. And their semi-major axes lie along the same line. As I've indicated in this picture, if I did carefully, both semi-major axes lie along the same direction, lie along the same line. So as we saw when I was playing the simulation the last time, where they had the two masses dancing around the center of mass, at all times as they move, the line joining between them passes through the center of mass. So they're always pivoting around the center of mass as they move around the center of mass. So they have the same shape, it turns out. They both have the same eccentricity. Their semi-major axes are lined up. And from the definition of the center of mass, we can figure out the relative sizes of their orbits. In other words, what we will find is that if one mass is 3 times that of the other, then its orbit is only 1/3 as big. That the mass ratio is the reciprocal of the semi-major axes of the ellipses, that ratio. How can we show that? Is trivial. With the origin at the C of M, center of mass, origin at the C of M, we have M1R1 plus M2R2 is equal to 0, because the definition has over M1 plus M2, but that would be equal to 0, so you can just multiply through by the denominator M1 plus M2, and just get M1R1 plus M2R2 is equal to 0, if you put the origin at the center of mass. So in other words, here's the center of mass, and it's always true that center of mass lies along the line between the two bodies. So if the center of mass is what we call the origin, at the center of mass there's R1, there's R2, the position vectors of the center of mass frame, and M1R1 plus M2R2 has to be equal to 0. So which one of those bodies is more massive as I drew it? M1 is more massive, it's close to the center of mass is closer to M1. So M1R1 is minus M2R2. The minus sign needs to be there because the vectors have to be pointing in opposite directions, on opposite sides of the center of mass. So if the center of mass is the origin, the two position vectors have to point in opposite directions, so we need that minus sign there. And if we take magnitudes, this says M1 times R1 is equal to M2 times R2, where by R1 I mean the magnitude of the vector R1, and by R2 I mean the magnitude of the vector R2. So if I take magnitudes, then I can get rid of the minus sign. So M1R1 is M2R2. In terms of just distance from the origin, M1R1 from the center of mass, M1R1 is M2R2. Or in other words, R2 over R1 is M1 over M2. At all times as they're moving around, the ratio of their distances from the center is the reciprocal of their mass ratio. At all moments that is true, that R2 over R1 is M1 over M2, which is just saying.
This is only the case when the center of mass is the origin.
Yeah, it's only when we put the center of mass at the origin, which we're always going to do. It's the smart choice. If we were studying a binary system, two objects orbiting one another, the most convenient choice is putting the mass at the origin. But it only works then because, you know, if I put the origin on Alpha Centauri, then that ain't going to work. The position vectors are almost equal if I put the origin on Alpha Centauri, but if I put the origin on Alpha Centauri, I'm an idiot. But I'm not an idiot, so I put the origin at the center of mass. Maybe I'm an idiot, but not for this reason. So, don't ask my wife.
That's what I'm saying.
Yeah. Is your husband an idiot? Never ask her that.
Hold on, let me get my notes.
Yeah. Yeah. Now, at some point, they're the semi-major axis distance away from the origin, somewhere along the line, because the orbits are the same shape at the same moment, they'll be their respective semi-major axis distances away from the center of mass. So we can also say that A2 divided by A1 is M2 divided by M1. In other words, the ratio of the semi-major axes is the reciprocal of the ratio of the masses. And as we already know, this is saying the larger mass moves on the smaller orbit. And in fact, if one mass is twice the other, then its orbit is only half the size. Yes?
Is that supposed to be?
It absolutely is supposed to be that. Yes, thank you. Because that would totally not make sense. Yeah. the larger mass moves on the smaller orbit. So as we've been building up to with great excitement, never going to see that piece of chalk again. I guess in principle, every once in a while we actually have a chalk picker.
Do you?
We do.
Oh.
I know, yeah.
Science.
Oh, yeah, it's like, this is like,
Okay, that one question.
chalk picker.
Chalk picker.
Science.
You do? Fine, I'll show you.
Alright, you convinced me. Let me bring it.
Oh, fine.
Whoa. The claw.
Big wall, that's great.
I swear, if you would have validated facts, I would have laughed so hard. Just not even paying attention, just like.
Wake up!
That's right.
Grab
This is dangerous.
A real professor would use that to write notes.
You get a real short professor.
Yeah.
Just write the whole lesson plan up there.
Yeah. Yeah.
Or didn't you?
Well,
I don't think they ever erased that part of the boards. They might be very confused.
one time I wrote "Hi Marcia" on the top so that Marcia, who was cleaning the boards, would be like, curse it.
Damn you, Doctor.
She did mention it to me the next day. And then I cleaned it. Anyway, so let's be specific here. In the equivalent one-body problem, A mass mu equals m1, m2 over m1 plus m2. I mentioned that before. I call that the reduced mass. Orbits a fixed mass. M equals m1 plus m2. Now, if that were the real system, mu and big M would have to move because it would have a force on it. But in the equivalent one-body problem, it's kind of artificially the case that big M actually just sits there. So we need to use special space-time nails to keep it from moving. Say that with a straight face, but it's artificial. It just sits there at the origin, and mu moves around it under its gravitational influence. So, for convenience, we'll put m at the origin. System mass. And the location is getting too low on the board, so I'll just move over here. The location of mu relative to m is the same as the location of m2 relative to m1. In other words, mu is located where somebody taking a ride on mass m1 would always be seeing mass m2. It shows their relative displacement from one another. So, the position of mu and its orbit about m is the same as the position of m2 relative to m1. In other words, the position vector of mu is in fact r equals r2 minus r1. And its velocity is v equals r dot equals r2 dot minus r1 dot, or in other words, it's v2 minus v1, which is the velocity of v2 of m2 relative to m1. Relative velocity of m2 with respect to m1. Right time.